Ja. Skal du sjekke eller da?
Det ser bra ut.
Ja, nice. Ja, skal bare holde tida også, tenker jeg. Ja. Are you start when? Yeah.
No.
Yeah,
Please
awesome.
welcome Martin.
Yes, hello, my name is Morten Linderud. I'll be talking a little bit about hardware-backed SSH keys today. So we'll be taking a bit look at how TPMs work, how SSH agent works, and my sort of hacks around those things. My name is Morten Linderud, as I said. My nickname is Foxbaron. I've been doing open source software development for almost a decade now, or a little over. I'm an Arch developer since 2016, and I'm also part of the board of Hackeriet, which is Oslo hackerspace. When I don't do open source stuff in my free time, I work at the Norwegian state broadcaster, mostly doing sort of infrastructure DevOps talks. My main interest is usable security tooling, so I've also been writing a bunch of like secure boot tooling, SBCTL, and some other TPM things. So why do we care about hardware-backed keys? Why are these things important to us? So the main thing we care about is key compromises. The reason for that is that if our keys or our tokens are leaked, somebody else can impersonate us, get access to our servers or something else. And this is not limited to SSH keys. This can happen to access tokens, cookies, anything that's on your hard drive that you're not protected. And the way, and to demonstrate this actual problem, there was a Born Group breach last year where somebody got access to an SSH key and managed to hack some servers based off on privileged access through some CI systems. You also had GitHub that got their RSA host keys leaked, which meant that you can impersonate the github.com SSH server because that's how we trust them. And sort of how do we usually go about protecting our keys or SSH keys? Well, we could be using YubiKeys, which are cool, neat devices that probably a bunch of us have. But my main issue with them is that they're expensive. A bunch of people, you need two, that's suddenly 100 euros. People think that's a lot of money for sort of hardware tokens. So clearly we sort of can do better, like we have something in our machines that everybody can use today to protect their keys. And they're called trusted platform modules. So these things have sort of been widely distributed and used in sort of machines for the past decade. They are secure crypto processors, so they do key generation, they do sort of signing attestation. They come in two variants, a discrete TPM, which is sort of a separate hardware device on the motherboards. And then you have the firmware TPMs, or the FTPMs, which are implemented as part of your CPU or your CPU secured processor. Intel has, not SGX, but the Intel ME, I think it implements it, and we have the AMD Trust Zone stuff that implements the TPM as well. TPMs give you a couple of features. You get platform integrity, which I'll show quickly, and you also have hierarchies and keys. And you also get some attestation features to make sure that you're talking with an authentic device or you're able to sort of differentiate between separate hardware devices. Platform integrity comes mostly in the form of PCR registers, and each of these registers hashes one part of your operating system during boot, during runtime, and we can sort of make keys and stuff only open if these hashes matches. If you're curious about these numbers and what they mean, the UAPI group has a sort of a list of all of the different registers and what they hash during the boot chain. We can also do keys and key generation. TPMs are sort of not that powerful devices, so we need a way to sort of make keys without actually like storing them on the TPMs. So what we have is three different hierarchy seeds in the TPM, which runs through a key derivation function. And this allows us to make sort of a bunch of keys on a low-powered device without really like having to store them anywhere. The hierarchy keys are as follows. You have null key, which is the session key. That's unique per boot. You have the owner key, which is unique, the owner hierarchy, which is unique for the device owner. So anything you make under owner hierarchy, you reset it when the device gets a new owner. And all of the keys below that hierarchy is, well, useless. You also have the endorsement hierarchy, which is for the lifetime device, which allows you to uniquely chain back the device back to some manufacturer, and you can make assertions on that. So the shielded keys are keys that we can make on TPM. We can then take them out of the TPM to prevent storing them, and then they're securely packaged and can only be decrypted by the TPM itself. The way this works with the TPM to toolchain is that we create some, this is the endorsement hierarchy, we make a context, we create a new key below this primary context, we load the key, we can make some message, and then we can sign this message with our key, and then we can verify the signature. That's sort of the basic things about it. We also have TPM policies, which can restrict our usage with different PCR values and system state. This is now sort of being implemented in System D, called PCR lock. So yeah, TPMs, slow devices, not little bit limited cryptography, that's the main thing, not quantum resistant yet, which is a little bit of an issue, and they're not really that much of friendly tooling built around them. They're also not natively supported by OpenSSH. So how do we make them supported by SSH? We do this through the SSH agent interface. So the agent interface can hold private keys for SSH. It has sort of a fairly simple Unix socket API you can use. It caches passwords, and you can offload key operations to the agent. The way this works is that we make an SSH agent, we add some ED251 key, and we can list the key. Further, when we want to use this key, if we actually specify the public key instead of the private key in the configuration and the SSH command line interface, the SSH will actually go and fetch the key across to the SSH agent instead of doing the key operations itself. And then you can also use that to SSH around. So this is agent protocol is implemented fairly well by Go library under crypto SSH agent. It's part of the extended open source library, standard library for Go, and sort of does all the things we need. It does key signatures, key listing, and can interact with all of these things. So I started hacking on SSH TPM agent 1.5 years ago. It's an agent that does TPM keys, fairly simple. So yeah, it supports key generation of RSA 2048 and then list mainly P256 and P358 keys. You can also do things like importing existing OpenSSH keys and sealing them to a TPM. And this is using the Google Go library called Go TPM, which is a native implementation and doesn't rely on the existing C libraries for the TPM. So the way the agent works is that we specify some socket location, then we start the agent. We can then do the normal SSH TPM key generation, because mirroring the existing usability of SSH is practical if you want to have people use it instead of reinventing something new. And then we can then add the key to our agent. We then export the SSH auth socket to our agent, and then we just list it as usual. So it just interacts with SSH as you would expect. We can also make an SSH key by default from normal OpenSSH, and then we can use the -- import one to sort of take the existing key and seal it to our TPM, which allows our machine to be the only one that unlocks the blob. So the way this works is that we can run the SSH TPM agent. We then do keygen of some ED DSA key. We don't give a password because we don't currently care that much about it. And then we have a new key, which is here. So this is sort of a secure blob. You can't really do anything with it. And then we can sign, and then we need to load it into our agent. And then the SSH command line interface is going to detect that key. And then if we sign it, no, -y sign, then we can write a signature with the normal sort of SSH key again -y, and it's going to use the TPM backed key instead. And then if you do the no check validate thing, it's going to say it's a good signature. You can also, so the key generation here is sort of, each new key is unique, it's a unique thing, but we can also make keys from the different hierarchy seeds. So here we can preload the assigning key from the owner hierarchy. Then when we call back on SSH, we get the hard-coded owner hierarchy keys. The cool thing here is that these are unique per device in this case. So even if you do a complete reinstall and run the same commands, you'll get those keys back. Yes, and this is practical for like host keys, because then you can't extract them from the device. You can't like take them away, use them on another device, and then make people impersonate. You have to have live access to the device and sort of funnel around things. You can also do remote key wrapping. So imagine you are some company that has SSH keys, and you want to provision them to your client machines. On the client, we can make an SRK, which is one of the hierarchy keys. We can then, on the remote side, we can make ourselves a new key, an ECDSA key. We can then wrap the SR key from our client machines with the key we just generated. And on the client, we can import that key, and it's only that client that can actually use that key. And that's useful if you want to sort of do remote provisioning. Yes. It also has host key support. So here we do the -A, which does the normal SSH host key generation that you expect. I then have a shortcut to install some systemd service files. And then we can then do a SSHD configuration file. If we then start the socket and then restart SSHD, we then have a small binary that lists out the keys we need or are curious about. And if we do a key scan, we have the key delivered from the SSH client. And this is useful because then you can't really export the key, or you can't do impersonation of the device itself. Yes. We also have some other sort of cool features. So we have, yes. So MC presented the Teletis key, which I have a unit of here. So let's imagine we have a Teletis key here, and then we start another SD agent. So one of sort of the annoying things is if you have multiple different agents with different keys, you need to sort of juggle around socket files. So I have a proxy support in the agent, so we can give our TPM agent access to the Teletis key socket, and then when we do -L, it's going to load the app to the Teletis key, and then ooh, exciting. No? Loading signer app.
It's loading.
Slow. There we go. And then we have the T key. And if we do now another key, and we add it to the agent we have, you're now going to see that it both shows you the TPM agent key and the Teletis key itself, and you can sort of use this one agent as sort of a proxy to different agents instead of sort of juggling sockets. All of this is made possible with sort of the TPM 2.0 key file spec. It's written by James Bottomley, currently not standardized, but it's sort of an ASN1 specification for how to sort of deal with TPM keys. So I did a bunch of work on this, or not a bunch of work, but I implemented this in Go. And it has several support cases, so the Linux keyring supports it, and the OpenSSL TPM provider supports it. And it's basically an AS-in-1 format for TPM keys. It supports loadable, importable, sealed keys, and you can sort of do different things with TPM keys. So I wrote a library for that, so you can use it in your Go stuff if you do Go. And then it interacts with OpenSSL, so you can do the TPM2 provider from OpenSSL, do some key that you want to create, and then TPM key again is going to understand that key, which is quite useful. So one of the interesting parts, though, is it secure? So let's see. I had problems with the internet today, so we'll see if this actually works. So this is my GitHub account. I'm going to prove to you if I have, okay, there's no agents. So I'm going to SSH into my GitHub account, and it should deny that. Permission denied, awesome. So we're going to create a new TPM key. What's a secure password? No, 1, 2, 3, 4. And we do the same again, 1, 2, 3, 4. Awesome, we have now made a key. So we're going to take the public key. We're going to do a new key. And this is the part where I should have found my... I should have put it in my pocket, but I didn't. Ooh. This is secure, I promise you. Use security key, push the key. There, it's added. So now we do TPM add of the TPM key. We SSH to github.com. Oops. And it should work. 1, 2, 3, 4. It works. You have access to my GitHub account. And if anybody's curious, that's the key. I'll give you 3-4 seconds to type it out or copy it or something. It's there. And if you're curious, I've done this before. This is a key from August 31st, 2024. Here's the QR code. That's a password. It's still there. Hasn't been accessed for half a year. And I've done this 3 times. So it just works. Or not works. It's provable secure in some way, maybe. Some improvements. I would like to do some more TPM policy stuff. It's a bit, if you've done TPM policies, a bit finicky with how PCR locks and stuff works. So I want to do some integration towards systemd PCR lock. I want landlock support because I want to sandbox some of the parsing system stuff we do. But it turns out it's a bit hard when you call external binaries. I was also supposed to do a 1.00 release before this talk, but I got stuck playing games instead. So that was poor planning on my end. And if anybody thinks this is interesting and has some feature requests, feel free to give me a feature request. I've also done talk at All Systems Go, so if you think TPMs are cool, but you also care about attestation or having some form certificate authority things, I talked about that part in September, which is basically sort of a how do you provision short-lived SSA certificates bound to the TPM. Yes. So yeah, that was my talk. Thank you very much for having me, and probably time for some questions.
Thank you. Seven minutes for questions.
Cool. Sure.
Can you limit the accessibility of the TPM somehow to a container setup or into specific containers or something like that? I haven't played around with that.
I don't know. I think so there's a TPM resource manager which should make like some of the TPM stuff invisible for some processes, so it sort of hot reloads TPM state, but I'm not quite sure how that works, so I'm a bit unsure. Yeah.
How
how many keys can your average TPM store?
The TPM doesn't really store keys. It has 3 seeds and then does a hierarchy key derivation function instead. So you can make as many keys as you want. The actual question though is how many keys can you load at the same time? And when I did the hierarchy key stuff, I loaded the RCA key and the ECDCA key at the same time. Turns out the TPM doesn't really like that because it has limited memory and starts giving me weird errors. So I need to figure that part out. So we can make as many keys as you want, and the second you sort of rotate one of the seeds, those keys are unusable by the TPM or your machine. Yes? Yeah.
When you say seeded keys,
Yeah.
why the keys are redundant back to the machine?
Yeah.
Why so?
So the reason they do this is because the TPM is a super small and low power device, so you can't really store everything. So what they do instead is that you can just load a couple of keys, but everything you load you can encrypt it on TPM and then take it out, and only the TPM with the seeds can decrypt it. And
Because we saw the private keys.
yeah. And if that's some sort of, I forget how it's, but it's some AES encryption with some key derivation stuff. So if you manage to break it, a bunch of other things are broken. But it's sort of a protection of the secret key material, which with the secret stuff being derived from the hierarchy stuff.
So
It's a bit.
the private key we saw
Yeah.
on the screen wasn't encrypted.
No, it's only unsealable by the TPM. But if you manage to break the